Okay, yeah, that's what it looks like. So that's fine.
So how do I get rid of this thing at the top?
Okay.
Good thing about
There you go. Yeah, that's what I did with mine.
Yes. We got one spectrum per band.
Early in the night or late in the night? You were still, you had to be there all night. I'm sorry.
Do not get sufficient right now. No, interesting. What? Oh, come on.
Okay, let's get started. We are here for Will's best thesis presentation. As is customary, Will's been supervised by Gene and myself. As is customary, we'll give a short introduction to those of you who don't know Will, to get to know him. Gene was observing last night, and I think he just woke up after a few hours of sleep. So
We actually got a spectrum, one spectrum with that. Take that, Hercules.
Yeah, so I'm left holding the bag to do the introduction, or as the honors, as the case may be. So I will briefly say a few remarks about Will.
You always do a good job,
Let's set expectations low here. As is customary, it's nice to say a few words about your students on their way out the door. And also, as is customary for most faculty, what you normally do is, the morning of the talk, you go to Google and you desperately type in your student's name and see what comes up, right? You never know what you're going to find. And I just want to point out to students who are working with me now is that I don't do this until the end of graduate school. Like if you're interested in working with me, I do not type your name into Google. Okay, so don't worry about whatever it is you've done in the past. You're clean slate to me. Okay, that's fine. Until the end. All right.
You put on safe search.
no time. All right. So if you actually go into Google and you type this, one of the things that comes up right at the top is this thing. So it turns out that Will is famous. He's in the Sun. Okay, and the Sun asks, a UK newspaper, who is Will Best? Dance presenter and former T4 on the beach host. All you need to know. That's pretty good. And then I was alarmed, deeply alarmed, to actually read the lead of this article. It says, Will Best is moving on up now that he has bagged a slot in ITV's Dance. And I'm thinking, hey, wait a minute. He's got no degree yet. He's not going anywhere. Not yet. All right, so hold on. Internet is wrong here.
PH Dance.
PH Dance, exactly. A bit of history about Will now is, as some of you know, Will, prior to coming to graduate school, had actually a very long, successful career as a teacher at nearby Punahou School, just down the road here. It actually amazes me. I still run into people randomly who went to Punahou, playing basketball with someone. They said they went to Punahou, and I mentioned, oh, do you know Will Best? And their face lights up. What a wonderful teaching experience they'd had with him as his math teacher, or so forth. But after 15 years at Punahou, Will got kind of tired because the buildings were all crooked at Punahou, and so he decided to try something else. So in 2010, I made contact. Well, Will actually made contact with me. Okay, and this is Proto Will here, contemplating perhaps he could explore his childhood interest in astronomy. And actually, I met Will through my wife. A co-worker of my wife actually was. Anyways, so small world of wifing. Okay, so Will set off for this marvelous adventure in graduate school, and who knows, where it will take you. And I should say that actually it's been a wonderful experience supervising Will. He's been very intrepid. He's a very stable guy, as you can see, not only physically but also, personally as well. That's been great satisfaction. And I think we've done really enjoyable science together. In his time in graduate school, he's been a wonderful producer of science, of which he will be telling you about today. And he's published quite a bit. He's going to tell you about some other stuff that has some papers in the works. But he's done other stuff as well while in graduate school. Not only has he been a producer of science, he's also been a great producer of music. Okay, and I don't quite know who his friends are, the Wicked Witch of the East, don't tell his wife, all right? And also along the way, he's also been a producer of humans. One human that I know about at least. Okay, so congratulations. But of course, time, all things must come to an end, and even graduate school must come to an end. And so at the end of this path of graduate school, Will has, he's at the verge of leaving. He's looking for his new path, and his new path will actually, he has a postdoc at the University of Texas. Seems like everybody in my group ends up at the University of Texas, so Will is continuing that tradition. But we'll see. Okay, so he still has to prove to us, you and the committee, over the course of the next 1 to 2 hours as to where that may be. Actually, if you look at Wikipedia, another search that comes up, you can actually see here, Will Best, of course, is an incredibly common name. But you go through the names, English cricketer, composer of For Sentimental Reasons, very nice song. And at the bottom, it actually says the most recent one is actually Will Best, 2011 present graduate student. Okay.
I do not know about this page.
And so I think for the next hour to 2 hours, we'll attempt to prove to us whether we should edit Wikipedia to say actually Will Best PhD strong. Okay, so take it away, Will.
Thank you, Mike. Let's see here. I believe you need to stop sharing your screen. There we go. Thank you. Yep.
Good.
No. Probably don't need to see that. All right. And I will note that my daughter, who you saw on there, my daughter Hazel was born on the day that Tropical Storm Ezel came through 4 years ago. So nothing can stop me. Thank you all for being here. Thanks especially to my committee members who were observing last night, even though they were getting wiped out mostly, and joining from California and from France, where it's rather late. So let's get going. My thesis combined something old with something new. Demographics has been part of astronomy for a long time, counting stars and galaxies to infer the formation and evolution of a population. But the new thing I'm bringing to this here is ultracool dwarfs. So these are the lowest mass stars and brown dwarfs, spectral types M6 and later. Of course, they're not totally brand new, but we didn't start finding the very latest M-type dwarfs until the late 70s and 80s, and the brown dwarfs in large numbers only about 20 years ago. So these are the objects now that we now know about that sort of fill a continuum of masses down from the lowest mass stars to the giant planets. So studying them, we get clues about the formation history and the evolution and the properties of stars and planets. Now this is a temperature sequence, as you see there, and also a spectral type sequence, but unlike with hydrogen burning stars, the key attribute of brown dwarfs is that they cool down as they age. They don't internally produce energy, at least after maybe the first couple million years. So this is also an evolutionary sequence for the brown dwarfs. They progress through L, T, and Y. So you're not looking at a simple mass sequence here the way you would be with main sequence stars. And I'll say a little bit more about that and what it implies. So I'm showing you here 3 different cooling curves for brown dwarfs, the temperature as they age. And let's say that you observe a 2000 Kelvin ultracool dwarf, and that's spectral type about L2. And what you can't tell immediately from looking at it is it a very young 10 Jupiter mass object, or perhaps a slightly older 150 million year old 40 Jupiter mass object, or perhaps it's even a very old 75 Jupiter mass star that has only just made it down to the main sequence. So we don't distinguish these things directly beyond maybe some clues for very young objects from the spectrum. And of course, those are just 3 curves. There's lots of different curves and objects of all different masses. And so there's an observational degeneracy between masses, ages, and luminosities, which creates a complex, tangled relationship between the observables and the physical properties. Even something as basic as the age distribution of ultracool dwarfs in the solar neighborhood is a very non-trivial challenge. And one distribution, another one we'd really like to measure, is the initial mass function. So if the galaxy is going to make a bunch of stars, we know it doesn't make them one at a time. It takes a large cloud of gas and dust and makes a lot of stars at once, maybe 1,000 or 100,000 solar masses, basically all at the same time. The IMF, the initial mass function, is the distribution of the masses of these stars. So how many high mass stars, how many middle, how many low mass, how many brown dwarfs. And we can express it with this particular expression here. The slope is the power law, and that alpha exponent is the key parameter. And on the right, I'm showing you some IMF determinations or parameterizations people have used before. Key result for the higher mass stars, down at the bottom right there, is alpha is about 2.35, indicating that as you go to higher masses, the number of stars drops off rapidly. That's the famous result from saltpeter, which has been found to hold in many other places, star clusters all over the galaxy, star clusters in other galaxies, some higher redshift galaxies, not in the most extreme environments, but as a rule of thumb, it's held up very well. There is much less certainty for the ultracool dwarfs, because we know that the general agreement that the slope flattens out and perhaps turns over as you go toward the lowest masses. But there's been different values for alpha people have found. There's perhaps a different functional form, and there's not a lot of resolution or constraint on this. And the field population, all the stars and brown dwarfs near us, have been forming for the age of the galaxy, 10 billion years. So there's objects of all ages, which we can't infer directly from observations. So you can't just go out and observe the IMF. You have to do something else and back it out. And one way to get at that is to build models. You assume an initial mass function, you assume a star formation history, and you predict what you should see. And this has been tried before. So here's a sampling of some of the results people have had. The Krupa papers are famous ones, and he estimated for the lowest mass stars and brown dwarfs. That's basically brown dwarfs, that mass range, about 0.3, so quite a bit less than 2.3, but with a fairly large uncertainty. Allen et al. Confirmed this with some Bayesian inference. More recently, there have been a good number of attempts to look at ranges of spectral types, look at the population as we've learned more about it, and the census has grown. And you'll see there's not a lot of agreement or particular strong constraint there, but generally people have found 0 or less more recently. So a negative alpha indicating that you are declining in the number of brown dwarfs as you go toward lower masses. So why is there so much uncertainty? Why is this so poorly constrained? One big reason is the lack of a well-defined sample. So a sample where you understand the biases and can eliminate them or get it as bias-free as possible. What was missing was a large volume-limited sample. And what's great about those? Well, they are the gold standard for population studies because you simply take all the objects in a volume of space. You're not worrying about magnitude limits or other selection effects. You minimize those as much as possible. And if we want to understand formation history, evolution, atmospheres of objects, you can learn a lot looking at individual ones, but for the complete picture, you need the whole population. And that's what's represented by a volume-limited sample. In order to define a volume-limited sample well, you really need parallaxes. These give you the most accurate, precise measures of distance, so they can determine the membership of a volume-limited sample most accurately and also give you the best luminosities. Well, what volume-limited samples are available? As of several years ago, not a lot. There was the Reed et al. Sample from 2008, which was a great step forward in its time, but it was mostly M through L, about 6 dwarfs, and contained in the L dwarf regime less than 100 objects. 2/3 of the distances were not parallaxes, they were photometric distances. There is an 8 parsec sample that's pretty complete from Kirkpatrick et al., but it's only a handful of objects, about 35 objects. So we wanted to do better than this, get a larger sample with more robust statistics. And that was the main target of my thesis, build in a much bigger sample that we could analyze for L and T dwarfs. So repeating what I just said, construct the first volume-limited sample of ultracool dwarfs within 25 parsecs, spanning a wide spectral type range, so covering some of the very lowest mass stars down to about L4 is the brown dwarf boundary. Above that, you might have brown dwarfs and stars mixed together, but everything beyond that is brown dwarfs. Roughly 400 objects, and again, defined by parallaxes, making a nice complement to the optical parallaxes for stars from Gaia. I'll say a little bit more about that later, too. So, steps to assemble this catalog. First thing we did was we, surveyed the landscape of papers. What's the census? What do we already know about? What might be missing? And which of the objects already have parallaxes? So this effort led to a large catalog we published from the PanSTARRS 3Pi survey, which covered everything north of declination 30 degrees for 4 years. Within that, there were about 1,500 LMT dwarfs, and our catalog also included more than 8,000 M dwarfs. There's many more than that even, but we had a good representative sample. And in particular, photometry spanning up to 11 bands from about 0.5 microns up to the 12 micron of Y. So a large range of photometry, very useful for any ultracool studies anybody wants to do. So from this effort to compile this catalog and everything that was known, what did we find? Well, as of about 4 years ago, we knew quite a few LMT dwarfs, but not too many of them in gray there with parallaxes. And you'll notice in the middle, there's kind of a divot here. Oops. Jumping ahead there. There's a little bit of a divot in the census here. This general region is called the LT transition from L into T dwarfs. And we expected that there should be somewhat lower numbers in there because it is thought to be a faster, shorter-lived phase of evolution, but not a divot this big. They should have found a few more. So this is where the census was least complete. This is where objects were missing. And we needed to address that. And I want to say a little bit more about the LT transition as we step into that. So here is a color magnitude diagram in near infrared showing ultracool dwarfs. So on the right going down, this is a sequence of late M into L dwarfs. And remember, for brown dwarfs, this is also an evolutionary sequence. So objects move along this down the L dwarfs. As they become T dwarfs at the transition, they become quite a bit bluer, and in J band, even a little bit brighter. And as they reach mid-T dwarfs, they then drop off rapidly in luminosity. So why this particular evolution here, which is this bluer turn, is really unique? Well, the spectra are changing considerably. I have L5 at the top here, down to T5, so that's through the transition. And you can notice this is the H band here. On the right-hand side of the H band, you have a nice peak there that just goes away completely as you go into the T dwarfs. That's methane appearing. It's also thought that L dwarfs are cloudy, and that those clouds disperse in some way in the LT transition, and T dwarfs have clear photospheres. So there's drastic changes here that are a challenge for modelers. And of course, this is also the location of our incompleteness in the census. So we really need to look for these objects. Why was the census incomplete? Why had people had trouble looking for them before? Well, these objects are brightest in the near infrared, so people had mostly used 2MASS to look for brown dwarfs. J-K color here for different ultracool spectral types. And if we zoom in on the LT transition colors right here, they're the same colors as M and early L dwarfs. There are a whole lot more M and early L dwarfs out there, and you can see them much farther away. So it's basically a sea of background contaminants. And finding LT transition dwarfs was real needle in a haystack work. So we brought new tools to this. We brought the PanSTARRS survey, and we brought WISE, the combination of optical plus mid-infrared, and the added depth of PanSTARRS over the previous best optical survey, which was Sloan. Led us to be able to distinguish these objects, in particular using the Y-W1 color on the horizontal axis. So that black cloud down on the the lower left there is gazillion M dwarfs, but Y minus W1 really helped us separate out the late L and early T dwarfs. And using this, we were able to discover quite a few new LT transition dwarfs. Pick your favorite one there. And that enabled us to fill in that gap nicely and say, yeah, now we have a pretty complete consensus. Next step towards building this picture, or this volume-limited sample. Which of the LT dwarfs are binaries? This is important for accurate determination of both luminosity and mass functions, because if you have unresolved binaries that you don't know about, they are absolutely going to skew both luminosities and masses. Past studies had typically assumed a binary fraction from some empirical result, made statistical corrections in a sample, but high angular resolution imaging can resolve most binaries within 25 parsecs. You can identify them one by one. And many had already been imaged with Hubble or with using ground-based adaptive optics. So we initiated a parallel project using the laser on Keck to observe anything that had not been observed yet that was a candidate for our volume-limited sample. We've imaged 168 targets. I'm not going to go into detail about this today, but I will mention one thing. When you observe a lot of objects in a survey, you usually run into something interesting. So 2MASS day 1119, before we observed it, was already an interesting object. It was one of the reddest known ground dwarfs, and that red color was associated with youth. It's a likely member of the TW Hydrae Association. That's a nearby stellar moving group with some brown dwarf members, thought to be in age roughly 10 million years old. So that's young. And based on that age, there's a model inferred mass of around 6 Jupiter masses. Well, we observed it Thanksgiving night 2016, and it is in fact a binary. Exciting. It is the lowest mass binary discovered to date. Because it's a binary and there's a luminosity of 2 objects, it's probably actually outside the volume-limited sample. But oh well. So this was fun. Let's get to the main course. Euclid parallax program. So we observed all the L0 and T8 dwarfs without a parallax that were between -30 dec, that's defined by Pan-STARRS 3 pi survey's lower limit, and +60, which is the north limit of Euclid, that had a photometric distance within 1 sigma of 25 parsecs. So we're going a little bit beyond to make sure we're not missing something. And we've got it. We've got 348 new L and T dwarf parallaxes. Along with that, we got a whole lot of excellent J-band photometry. And we took the opportunity to clean up the photometry on the MKO system, H-band, K-band, Y-band, so that did that with some other observations and also with synthetic photometry and low-resolution spectra, so that we'd have photometry of the same quality as our parallaxes. To reduce the parallaxes, I substantially modified the pipeline that was originally written to produce CFHT parallaxes, which have been very successful with that. That was originally designed to handle 5 or 10 parallaxes at once. That wasn't going to work for my program because I was observing hundreds of objects, so it's now fully automated. Plug in images from Euclid, get out parallaxes in an absolute reference frame. And I'll mention that we implemented an iteratively reweighted least squares regression in order to get accurate solutions and uncertainties. This was also used in Pan-STARRS astrometry by Jean Magnier and Chris Waters and others. And this was a nice addition that enabled us to get uncertainties that we feel really accurately represent the quality of our data. So what does it look like? Well, here are the parallaxes, showing you the distribution. It's the largest batch of infrared T and dwarf parallaxes anybody's published to date by some measure. I'll highlight where 25 parsecs is. Anything with a parallax of 40 milliarcseconds or greater is within 25 parsecs. And you may wonder, why do we have so many that are outside 25 parsecs? Well, binaries will always get into magnitude limited samples because since you're combining the light of two objects, they'll be brighter and they'll appear closer than they actually are. And when our survey definition, our choice of objects was essentially magnitude limited, anything with a photometric distance out to 25 parsecs plus 1 sigma. So there were a lot of objects in that we did not know were binaries before we began the observations. And now that we've got parallaxes for them, we can see that they are a fair amount farther away. Parallax uncertainties are nice and small. This is really great since our strategy was to survey a large number of objects, get as many as possible rather than to aim for maximum precision. If we compare our uncertainties down at the bottom, median error is 3.5 milliarc seconds. Compare that to some of the other surveys that have been conducted. We're on the same footing with most of them, and we're really excited about that because while achieving the same uncertainty, we've been able to observe many more objects than previous searches. Here's the spectral type distribution. This is essentially what was needed to complete the sample. And you may be wondering again, where is Gaia in this? Gaia was observing 1.3 billion parallaxes. Did it get any of these objects? The answer is yes, about 100 of them. And there they are. Mostly the early L dwarfs. And Euclid filled in everything after that, which was too faint and red for Gaia to observe. And I'm putting on here that substellar boundary that I mentioned around spectral type L4, which really points out that Gaia is a survey for stars. 1.3 billion parallaxes almost entirely of stars. Studying brown dwarf populations requires infrared observations from the ground until we watch infrared Gaia. This gave us a great opportunity, though, to compare our parallaxes with the overlaps with Gaia, and this is the comparison here. We're doing well. All right, let's take a look then at our volume-limited sample. Here is the overall spectral type distribution, and I'm highlighting where the parallaxes are coming from, using if there's more than one measurement, just using the most precise parallax for each object. So again, you can see Gaia has contributed mostly early L dwarfs, and Euclid has really filled in the census with parallaxes for later type objects. There are a number of Gaia objects you can see at the lower right for very late type. Those are parallaxes for primary stars for which a late T-dwarf is a companion. So Gaia didn't observe those directly. Gaia observed, I think, a total of 8 T-dwarfs, pretty rapidly in most cases. All right, how complete is this sample? To assess completeness, we use the V/Vover VMax statistics. This is a classic test to see if a population is uniformly distributed. It was first developed for quasar samples and has been used in extragalactic studies quite a lot since then. But it works just as well for stellar samples. And I don't want to go into gory detail with it, but the idea is that a sample that is uniformly distributed in space should have an average V/Vover VMax statistic of 0.5, which means half of the objects are in the inner half of the volume and half are in the outer half of the volume. And if your V/Vover VMax average drops below that, that means you have fewer objects in the outer half of the volume, which is an indication that your sample is becoming less complete as you go farther out. Uniform distribution is a good assumption for our sample because 25 parsecs compared to the galaxy is really just a little bubble completely within the thin disk. We're not much impacted by scale height. So we're just comparing our samples of V/Vover VMax out to different distances. You can see like the trend, we're dropping slowly below 0.5 as you move further out. So maybe you've got 15, 16 parsecs. We can say we're pretty complete. Anything in the earlier part there, like 10, that wouldn't pay much attention. That's low number statistics noise. But we see a real trend as we go up to 25 parsecs of slightly falling off. About 85% complete at 25 parsecs. But we can look at this even, and there are error bars here. They're just smaller than the symbols. We can look a little more closely here at that 85%. If you break it down into some spectral type bins, we're actually quite complete for early L and early T dwarfs, maybe a little bit less for the later L dwarfs. For late T dwarfs, we are quite a bit less complete. This is something we expected because as you get to T6, T7, T8 dwarfs, at 25 parsecs, those objects are really pushing the magnitude limits of the surveys that were used to discover them, in particular WISE. So this is this is where our survey is going to be the most incomplete, just in those latest couple of spectral types. For other things, we're doing quite well, and we can use Vover VMax to correct numerically, statistically, for the incompleteness in the sample too. All right, so what can our volume-limited sample and our new parallaxes tell us about the population? I'm going to show you now color magnitude diagrams updated with everything. So these are parallaxes from the literature, and this is the same basic sequence that I showed you before. L dwarfs going down the right, LT transition crossing to the left, and later T dwarfs dropping down here. Now I'm adding on the Gaia parallaxes from Gaia, mostly in the early L dwarfs, as we saw in the histogram, and there's a few brown stars scattered in the lower parts. Again, those are companions to main sequence stars that have Gaia parallaxes. And now I'll add on the Euclid parallaxes, and you can see we've really filled in later L, T transition, and T dwarfs. So we can do a lot with this. For example, where do the young objects sit on a color magnitude diagram like this? You can see that green there, but they are mostly forming a sequence down the left-hand side. By young, I mean objects roughly 200 million years old or younger. Those really sit here on the right-hand side, excuse me, to the right of that sequence, indicating that in general they tend to be redder. It's clearly shown here. These objects down at the bottom are planetary mass companions, which are very, very red and faint. Okay, something else we can do. We can look for binaries, and this is important because if we want to get a clean evolutionary sequence on here, the photometry from unresolved binaries is really going to clutter that up. So we need to know where the binaries are. You can see they're distributed pretty much throughout. In the LT transition, they tend to be in the upper part of it. They're essentially puffing it up, and that's because you have combined light from two different objects. So see, there they are again. I'm just going to take them off. I'm going to take them out of the sequence so we can get a better idea of what this evolutionary sequence looks like. And that looks cleaner, although these are probably some unrecognized binaries up here still. But this is everything. I've been showing you parallaxes for everything we know. We have a volume-limited sample now. So what does it look like if I just stick within 25 parsecs? And what we see here is the same sequence, but there's now this gap that has appeared at the beginning of the LT transition, right? About there. Okay? So what's the gap? Well, it must be some phase of evolution that is very brief or skipped almost entirely, where objects reach the bottom of the L dwarf sequence and changes in their photospheres make them become very rapidly bluer, half a magnitude. In astronomical terms, almost at once. Okay? Why didn't we see that in the full population before? This has not been recognized previously. Why wasn't it seen? Well, when you're looking at samples of everything, you're including more distant objects, and that means you're going to get a lot more binaries in there. And the gap can be filled by binaries with an object from each side. The blended photometry can fill in that gap quite easily. So we needed a volume-limited sample with a lot of objects in order to see this. Now, I mentioned previously the LT transition has been a challenge for models. Is this gap predicted by models? Well, maybe one. So here's that previous color magnitude diagram I showed you with the basic evolutionary sequence. The Soman and Marley 2008 hybrid model is the only one that has been able to successfully predict luminosities for LT transition dwarfs that have known masses. So, showed you the model there. Apologies for one thing, I'm using on the left-hand color magnitude diagram. Get the cursor to appear now. Left-hand color magnitude diagram is using J-band absolute magnitudes. On the right, it's K-band absolute magnitudes. But it's the J minus K color that matters, not the exact slopes of things. Okay. But the hybrid model is, I should say, the Soman and Marley family of models from 2008 had successful cloudy models for L dwarfs and clear models for T dwarfs, and they essentially did a linear interpolation between the two to model the LT transition. So it's not purely from physical principles. No one's been able to do that, but it's a prescription that actually was successful in producing luminosities for some specific examples of LT transition dwarfs. So that model predicted a possible pileup. On that plot on the right, the red and blue dots are, and black ones at the top, are known objects at the time, 2008, and then the little green dots are the modeled objects. And they predicted somewhat of a pileup there. And 2012, Dupuy and Liu looked for this. I also looked for it in one of my subsequent papers. And there's a suggestion of a pileup there, and possibly a little gap afterwards. So does that match up with the gap that I see now in the volume limited sample that we have? Well, here's the color magnitude diagram again. I'm going to zoom in on the LT transition, and I'm going to overlay the hybrid model on the same scale. So there's my gap, and there's the pileup, more or less, for the Sullivan and Marley. So it remains a challenge. Perhaps there's something about the effective temperature of the interpolation that they used that wasn't quite right, or more to dig into. Just to highlight the significance of the gap there, you can see it really is a divot in the histogram of J minus K colors. Those errors, by the way, come from Monte Carlo simulations, bumping around the errors. So we see a good significance there. The gap that was seen previously by Dupuy and Liu, and also by my 2015 paper, there's something there, but it's a depression, maybe. I shouldn't use words like that with Olivia still out there. Okay. So now what can we learn about the population now that we've got this volume limited sample? Back to talking about the initial mass function and the birth history. Can we infer anything about these for our nearby 5 parsec sample of brown dwarfs and ultracool dwarfs? So what we did is we did some modeling here. We assumed, again, that form for our initial mass function, and birth rate expression I'm using is just an exponential e to the negative beta t. This has been commonly used in other ultracool studies, and it's standard in the stellar community as well. If beta is 0, then you get a flat star formation rate, stars forming at the same rate throughout the history of the galaxy, or it could slope up or down, depending on beta. I'll mention, as before, we also, for this analysis, we removed the binaries and Y companions because they may have different formation histories. We're looking at the population of single objects here. So from those forms, we can adopt a value of alpha and beta and use that to derive masses and ages from the distributions parameterized by alpha and beta. We can make a model population with masses and ages. Those are the things that we can't get at directly observably. And then we use an evolutionary model, again, the hybrid model, to derive luminosities and volumetric magnitudes for our objects. And then also have a volumetric luminosity function for our volume limited sample, and compare using chi-squared to the models. We can do this again for a grid of different alphas and betas, so lots of different parameter values there, and see which one is the best, gives us the best fit to our volume limited sample, the best fit alpha and beta, which would give us parameters for the initial mass function and birth history. This is pretty standard, is what's been done before. What's new is our volume limited sample. Here is, first of all, the luminosity function for our volume limited sample. The incomprehensible symbol over on the left just means the space density. Okay, so on the order of 1 × 10⁻³ objects per cubic parsec per magnitude, and then a distribution of volumetric magnitudes. And looking at this spot here, the last 2 bins, the faintest ones on the right, for those, those bins are based on only a few objects, only a handful, so we didn't want to include them in our analysis. Now, this of course needs context, like luminosity functions for our synthetic populations. So I'm going to overlay 3 of them here, and these are using different values of alpha for the IMF. All of them have a beta of 0, so assuming a constant birth rate. And you can see there's some differences between them, but as a whole, they match our luminosity function marginally. The overall shape is basically the same, but there's a couple of points of disagreement. That spike right there in the synthetic luminosity functions is the LT transition. And that basically spectral types L7 through T3. And this is not the small pileup that we were talking about before that might be in a different location. This is an overall general slowdown in the decline of bolometric luminosity at those spectral types. This is a known feature of the hybrid model, and it was what enabled it to successfully predict luminosities in some specific cases. But we're seeing that for the whole population, it does not match our observed function. And that spike appears in all our synthetic things for plausible ranges of alpha and beta. It's not just these three particular ones. And there's also a bump later on there at fainter objects. Those are late T dwarfs. And in general, we expect there to be sort of a pileup of late T dwarfs in any brown dwarf population because they are cooling down constantly. So warmer objects are always becoming cooler, and you expect to get more fainter objects. But what we're seeing is that in our volume limited sample, you get more objects in even fainter bins. The drop off in luminosity seems to be even more rapid than is predicted by the models. So there are still some issues here. And this helps us understand more about how brown dwarfs are actually cooling as they age. The previous data sets weren't really sensitive to these differences. But we've got now luminosity function with some error bars that is roughly on the same scale with the separations between models. So we can still ask which of the values give us the best match to our data. So again, a grid of alpha and beta compared using the chi-squared statistic. And at the upper left is the chi-squared surface. It has a clear minimum. That is really covering plausible range of values for alpha and beta. So there's one minimum there. And I marginalized over each of the axes in order to get a distribution for alpha at the bottom and for beta on the right. Best fit values we get, -0.46 for alpha and about 0.08 for beta. So for context, alpha, that negative alpha means compared to saltpeter or a positive value, fewer brown dwarfs of lower masses, a steeper decline as you go to lower masses. And for beta, that's consistent with being constant star formation history, maybe a slight decline. And particularly happy with the beta because essentially no one had produced a good numerical constraint previously for the star formation history. So this is really nice to see. Now, how about the IMF? I showed you a table before. I'm going to show you it again, listing different determinations of alpha. Add mine to it there. We're in good agreement with those who say, hey, alpha is negative. We've got a numerical constraint on it now. So looking particularly, this is a wider range now, though, L0 all the way through T8 dwarfs. With our large volume limited sample, we're adding some weight to that negative value for alpha. And our birth history, consistent with constant, first good constraint on this from this type of model. And I'll finish here with a nice little science nugget. Although we have good agreement with many previous estimates for the field, ultracool IMF, the stars and brown dwarfs that are nearby us, we have some disagreement with star forming regions. And this has been seen before, but we've got a bigger sample, so this is really interesting. This is a few, there are many, but this is just a few estimates looking at star forming regions. They are harder to observe because they are farther away, so if you're looking for the lowest mass objects, they're really faint, but you can model, you can do your best, and people have come up with some pretty decent constraints on alpha, and you'll notice they're all positive. They're one larger than my result. There is tension here that has not been resolved. Lower limiting. One possible resolution for this that I'm looking forward to exploring in the future, has the ultracool initial mass function actually changed in time over the galactic history? The field contains objects, formed from 0 to 10 billion years ago. So you're looking at a mixture of ages, and that will include older objects that perhaps formed with an IMF with a negative alpha. But star-forming regions is with star formation now, maybe alpha has somehow increased. And that would mean that the environments in which stars and brown dwarfs form are different now than they were earlier in the life of the galaxy. All right, to summarize. Discovered nearby missing LT transition dwarfs, filling in the census. We've measured the largest set of LT dwarf infrared parallaxes, about 350 of them. And this enabled us to create the first large volume-limited sample of brown dwarfs defined by parallaxes and nicely complementing what Gaia has done for stars, a little beyond 25 parsecs. We've found a large gap in the LT transition in J-K colors. That's not where models have previously predicted. We've identified also a problem with the cooling rate of LT transition dwarfs in the model that has been most successful at predicting LT dwarf luminosities. And we've found new constraints for the ultracool initial mass function and birth history in the solar neighborhood. And I want to say thank you to many people here. I have almost certainly left some names off. That's the inevitability of this. But many people have supported me throughout this long journey. But it's been great to work with all of you, and happy to take questions.
Thanks a lot, Will. That was really fantastic. And as traditional, we will now take questions from the non-thesis members in the committee, and we'll take questions for a little while. We have a bit of a constraint here because we have a colloquium at 9:45 in this very room. The thesis committee members will depart and let the colloquium continue on here while we continue to interrogate Will after the rest of the community questions. So let's start with questions here in the audience. I see Laurie.
Will, that was well defended.
Thank you.
I'm so excited about this possibility of a time-dependent IMF, and in particular, the volume-limited sample with the negative value of alpha. Can you talk a little bit about how this sort of turnover in the formation of very small bodies might relate to, say, the brown dwarf desert that we find around sun-like stars, or in other binary systems?
Right, right. So the brown dwarf desert is around main sequence stars. There is a real deficit of objects in the brown dwarf mass ranges relatively close in. I think it's within 5 AU or something like that. We find planets inside there, but not, when we find, smaller stars, but not brown dwarfs. There are two formation scenarios going on there, I think. One of them is brown dwarfs form in star-like ways, maybe as binaries, and you just have a very unequal mass ratio binary. And then there's also planet formation, which might be a colder start model where there's core accretion, and that's how you build up the thing. So I don't know if this has any implication saying that core accretion also could have changed in its scenario over time, because that would also be part of this question here. But I think you'd have to look at that, because if the environment for unequal mass binaries is changing, or single objects is changing, then it might also apply to planets. I hope that's answering your question.
Next, I think that's Mike back there.
Yeah, so if you slice up your sample into maybe some of these different ranges that other studies have looked at, how does that change like your alpha and beta?
If I just took off, if I say, let me just do the T0 through T8.
Yeah, if you just like slice it up into different subpopulations maybe.
That is a great idea. What I suspect you would find is that the T-dwarfs, the later T-dwarfs are the ones that are adding the most weight to the IMF and probably making it negative for two reasons. In general, because you expect objects to pile up in the later T-dwarfs because they're always cooling down and always evolving, but you can also get T-dwarfs by having just a lot of low mass objects. That late T range is really sensitive to what the IMF, what the parameters of the IMF are. And the other is that if you compare space densities that I measured in my sample compared to, say, the Metchev one, which is right about in the middle, that was approximately 0, my space density for T-dwarfs is lower. And it's more precise because I'm looking at a lot more objects. Metchev was working with just a small sample. So probably just doing T-dwarfs, you would almost certainly get a negative alpha. I'm really interested to see what would happen if you just do it with the L-dwarfs.
Next, more questions. I see. Oh, I see. Back there, Jamie.
Can you talk a little bit about what effects you expect composition to have on your assumptions about IMF?
Yeah. Metallicity is a great frontier in brown dwarf science. It absolutely affects what we see on the color magnitude diagram. There are brown dwarf subdwarfs for very low metallicity in old objects, and they are bluer and they are fainter. So that absolutely exists. In general, they have not been successfully incorporated into models, at least sort of the last generation of them. I think the new ones that are coming online have metallicity incorporated in, but the Soman and Marley models were all solar metallicity, and that was the state of the art at the time. So it must play a role, and I don't know what it is.
Other questions in the audience here, or any questions coming from Zoom land, excluding our committee members? If we don't have any more questions, oh wait, we do have one more question back there.
The gap that you discovered.
Yeah.
What's first of all, what's the approximate time scale for it? Would you estimate? And then, do you have any speculations what might be causing it? Extremely rapid clearing or what have you?
Yeah. Yeah. Okay. How long is it? That's probably a calculation I could do relatively easily, maybe not in 10 seconds, but just from number density and of surface density on the color magnitude diagram versus the evolutionary time scales. But we're talking tens of millions of years probably. As for sorry, what was the second part of the question?
Speculation on what causes it.
Right. Okay. So there have been several scenarios proposed for how you get from cloudy to clear. One of them is a sudden rain out, and that could happen. It could happen with certain species and not others, but those have different species of things in the clouds, which are like minerals, like this is at 1500 Kelvin or 1300 Kelvin, but minerals, and in some cases like liquid droplets of things, and methane, and and carbon monoxide, of course. And they have different effects in different parts of the spectrum. So in J-band in particular is sensitive to some of the clouds. A rain out would pop up the flux really quickly in J-band. That's a possibility. There's also been a recent proposal that it's not so much cloud composition and materials from clouds going away. It has more to do with the convective properties of the atmosphere, and you're seeing heat coming up in different ways as you go through this transition. So there might be, like at a certain temperature, you might get an appearance of convection cells that affects the photometry in some particular way. I would say this should be a subject of a lot of speculation.
All right, if there are no more questions, then let us thank Will once more. Do we have any questions in here, though? No, no more questions, then let us thank Will again. Now it is time for the examination.
Where are we? Are we in VCR?
We're going to do the VCR. Actually, I'm trying to get out here.